Okay, now we're looking at the last type of transformation, which is a shear. When a shape is sheared, it is deformed in a way that part of the shape is pulled more than the other. So part of the shape seems to be pulled more than the other. So if you look at our shape here, right? This is the original shape, and that's the image. It appears that this top part was sort of pulled more than this bottom part, right? Such that the bottom part will lag behind that one, right? So this thing is now sort of slanting, right? So shearing has a slanting effect on the sides because one side seems to be experiencing more pull than the other side. So that's basically shear. Now, whenever you're describing shear, right, remember you have a shape A being mapped onto an image B, and you're asked to describe the transformation. When you realize that it's a shear, you need to mention that it's a shear. You need to mention the invariant line, right? And then you need to mention the shear factor. So we're going to look at all that. We're going to look at the invariant line and the shear factor and what they really are. Okay, so let's have an example here. Let's say shape a triangle A. This is triangle A. Here's my triangle A. Experiences a shear, and the resulting triangle is triangle B, right? So this is triangle B, the green one. And triangle B and triangle A share the same base. So that's triangle B. So I had triangle A, and the image is triangle B. Now let's try and describe this transformation. What kind of transformation is this? Now we clearly see that this point was pulled to that point there, right? That's clear. But we see that these 2 points did not move, right? And every point on that did not move. So the first thing we know is, of course, this is a shear, right? That's the first part. But now we want to talk about the invariant line and the shear factor. Now, the invariant line, right, is a line on which points do not move when a shear happens. So when a shear is happening, there is a line on which points do not move, right? Sometimes part of the shape is in contact with the line. Sometimes no part of the shape is in contact with that line. So if we look at it, every point at this level here did not move. What level is this? If we map this out right through, we'll find that this is the level of the line y is equal to 1. So if you look at this, this is the line y is equal to 1. Every point that was in contact with the line y is equal to 1 did not move. Nothing happened to it, right? So this line y is equal to 1 is what we call the invariant line. So the invariant line is y is equal to 1. Right. In some cases, none of these points are in contact with the line y is equal to 1. So all points will be affected by the shear in that case. But in this case, part of the shape is in contact with the line y is equal to 1. Therefore, no change happens to all those points on the line y is equal to 1. So that's our invariant line. Now, as we study this shear factor, the shear situation, right? We want to see how we can calculate our shear factor. Now, from here to there was the shearing that happened, right? And from there to there, there's the distance of shear. So the distance from here to here is the distance moved by the sheared point. Then from the sheared point, there's another distance we need to take note of, which is this distance, which is the distance to the invariant line. So for every shear, you need to take note of 2 distances: the distance moved by the sheared points and the distance of the sheared points to the invariant line. So if you look at it, the distance moved by the sheared point is 1, 2, 3, 4, 5. So distance of shear is 5. And then distance to invariant was 1, 2, 3, which is 3. Now, when our shear factor is always distance moved by shear over distance to invariant line. So our distance moved by the sheared point was 5. Our distance to invariant was 3. So our shear factor was 5 over 3. So this transformation was a shear with an invariant line of y is equal to 1 and a shear factor of 5 over 3. So shear invariant line is y is equal to 1 and shear factor is 5 over 3. Okay, let's have another example here, right? We have a shape which is triangle X mapped onto another shape which is triangle Y. That is our image, right? So now what we realize is that the points, all these points here moved from this original shape to that new shape there, right? So if we look at this point here, it moved to that point there. So this movement from there to there, that's the distance of our shear, right? And it's from level 3 up to 7, so it's 4 units, right? What we also need to see is that on this point here, none of the points moved, right? Here. So this line here coming down here is our invariant, and it passes through 1. This is the line x is equal to 1. So this is our invariant, right? So we can already say that, okay, for the description, this is a shear, and our invariant line is x is equal to 1, right? Is x is equal to 1. Maybe this is not the clearest diagram, but it's x is equal to 1. Right? So now we want to calculate our shear factor. To calculate our shear factor, we need to look at the distance of shear and then the distance of sheared point to invariant. So this is the distance to invariant line of sheared point to invariant line, which is 1, 2, 3. It's from 4 to 1, so it's 3 units. So our shear factor is always distance of shear divided by distance to invariant line, which is going to be, in this case, 4 over 3. So 4 over 3. So that's it. You have a shear with the invariant line as x is equal to 1, and the shear factor is equal to 4 over 3.